Hi, thanks everyone to attend my presentation at icassp this year. And today I'm going to present the paper called Contrastive Knowledge Graph Attention Network for Request-Based Recipe Recommendation. First of all, let me briefly introduce the background of this paper. So in Alexa, Kitchen Assistant is one of the enabled services in intelligent voice assistant. So it's kind of an essential part in the Alexa. And the current solutions for recipe recommendation have two limitations. First, it neglects user personalized preferences. And second, there are some user recipe interaction noises there. For example, users may randomly or mistakenly click on some recipes. To tackle with about two limitations, we propose a contrastive knowledge graph attention network, which includes three components basically. The first one is a knowledge graph attention-based recommender. Second one, we profile the user diversified preferences from user historical behavior sequences. And last, a contrastive learning module with two auxiliary tasks proposed to improve the model robustness. And let me formulate the research question here. Given a target user and his or her utterance request, we aim to recommend the top K relevant recipes. That's the overall goal for this paper. And the information used in the proposed model includes the users and the recipes with textual and categorical features like the recipe name and the cooking time, and the user recipe interactions with a sequence of behaviors, like the users browse the recipe and then add the recipe to cart. And a recipe knowledge graph with recipe entities and attribute entities. Attributes may like cuisine, ingredients, keywords, and so on. So in the end, we merge all the mentioned information together into to achieve a collaborative knowledge graph. We call it a CKG here. And in this slides, let's dive deep into the model details. The CKGAT is the model we proposed in this paper. It consists of three components. The first is a knowledge graph embedding, leverages the structure of the collaborative knowledge graph to learn the entity embedding. And the KGAT-based recommender is proposed to learn the collaborative user and recipe embeddings by modeling the diversified user preferences. And last module is a contrastive learning module, contrast the user and recipe embeddings from different graph views to improve the model robustness. The three modules we can see it clearly in the pipeline shown in the bottom of this slide. First, let's take a look at the modules in the proposed model step by step. The first one is knowledge graph embedding. In each user recipe and attribute entity in the collaborative knowledge graph is associated with an ID embedding. And we use a trans-E to learn the entity embeddings with the typical knowledge graph laws here. And basically it wants to maximize the likelihood that hide entity embedding plus the relationship embedding is equals to the tail embedding. So this is the first loss we mentioned is a knowledge graph embedding loss. And the second part module is called KGAT rec. And to dive into the details of the KGAT rec module, we can see that in the collaborative knowledge graph, a user item or item collaborative embedding is updated by aggregating the rich semantic information from its neighbor triplets. So for example, if we want to learn the I3 is a recipe and is concatenated, is linked with a user and the two attributes. So we use attention mechanism and leveraging both the entity embeddings and the relationship embeddings to learn the different weights on the neighbors. And then we use the weighted sum on the neighbors to have a contextual embedding for the target recipe. And there's a different part here to calculate the relationship embedding between the user and the recipes. This one, besides the initialize the ID embedding for the relationship, and we also involve the user historical behaviors on the recipes. So the historical behaviors will pass to a GRU, and then we concatenate the GRU hidden states and the original ID embedding to form an updated relationship embedding. And after that, we will get the user and recipe embeddings, and we will use them to predict the binary relationship between them. And we update the target entity embedding by aggregating its entity embeddings and embedding of its neighbors. So we can see that the updated entity embedding is from both itself and its neighbors. And we stack and concatenate L layers to represent the user and recipe vectors. Besides these two vectors, we also use a bird to retrieve the user request vector. And final recipe vector is also the concatenation of its entity embedding and the feature embedding learned from the textual and the categorical features. Remember that for each recipe, we also have a categorical our textual features associated. And the final loss is a typical BPR loss. The last model is incorporating contrastive learning. It contains several steps. The first one is a graph augmentation. In the GA stage, the different views of the input graph are generated to expose novel patterns of recommendations to improve the model generalization. It contains two operations on the original collaborative knowledge graph, including a node embedding dropout, meaning we randomly mask some of the dimensions on the entity embeddings. And second is age dropout, meaning that we will randomly remove some edges in the collaborative knowledge graph. We apply the operations on the graph to generate two different graph views in the end. And the two different graph views will pass to the KGAT rec module to generate the recipe and the user vectors on each view. And then we will have two different contrastive learning functions to learn two different types of the loss. The first one is called unsupervised contrastive learning, and the info NCE loss is adopted to put different views of the same user entity close and push those of different user entities away. So it happens only on the user side, and it also happens on the recipe side simultaneously. So in the end, we will have a unsupervised contrastive learning loss. And we also have a supervised contrastive learning loss. So given an observed user recipe interaction, we encourage the agreement between the user and the recipe generated from different views. Meanwhile, we minimize the agreement between unobserved user recipe pairs. So it happens on the user and recipe on two different views, meaning that we calculate the SJL loss. It's still a info NCE loss, and it happens from the user vector on view 1 and the recipe vector on view 2. So in the end, we combined all those unsupervised and supervised contrastive learning loss together to form a final loss. And the model is trained by alternatively minimizing the final recommendation loss, loss BPR plus loss contrast learning, and knowledge graph loss during each epoch. And next, let me introduce the experiments. First of all, is the data set and the baselines we use in this paper. So we use Alexa data where customers can interact with devices equipped with screens by vocal request, which forms the recipe voice dataset. Or touching the screen which forms the recipe and touch dataset. The baseline we used contains a non-graph based and graph-based collaborative filter. They including 4 types of the 4 baselines, including YouTube DNN, Light GCN, KGCN, and KGAT. So we compare the model performances on all these baselines and our model, and the table shows the relative performance improvement afforded by our method compared to the all baseline models. It says that we use the KGAT as a baseline, and all the rest models shows the relative improvement on the KGAT. We can see that only our model has a positive value, means that our model can significantly beat the KGAT model. And the KGAT model is the best baseline model among their 4. We also have an ablation study to quantify the impact of the components in our proposed model and report the corresponding degradations. So including the GRU from a preference vector, the contrastive learning that includes both the unsupervised and supervised contrast learning, and our only use the supervised contrast learning, or you remove the node embedding dropout, our age dropout. So you can see that each component in the design model shows a positive impact, because after we remove them, we can see that there's a performance degradation. Also, we try to validate the model robustness by adding contrastive learning module. We train models with different ratios of additional noise data sampled from the unsupervised interactions and compare their performances. So we can see that if we adding more noisy data, all those models' performance are dropped, but our proposed CKGAT model still outperforms on all the scenarios, and it does not drop as much as the rest 2 baselines, meaning that our model is more robustness on the noisy data. To summarize, we propose a contrastive knowledge graph attention network for user request-based recipe recommendation. The proposed model not only boosts performance by modeling user preferences towards different recipes, but also integrates unsupervised and supervised contrastive learning to improve the model robustness. And in the future, we plan to improve the model performance with advanced negative sampling strategies and use some transfer learning techniques for cross-domain recommendation. And that's all for the presentation. Thanks again for to attend my talk here.